Alrighty. Perfect. 10:15. Oh, I'm back. Okay. So, welcome back, everyone. Just as people are trickling in, just wanted to know, are there any questions from stuff we did yesterday? We kind of talked about, physical properties changes, chemical properties, chemical changes, just general properties of matter, solids, liquid, gases, that sort of thing. If there's nothing, we will begin our math fun and talk about measurements. Chris, not necessarily. That's okay. You're totally welcome also to watch both. But this particular class moves a bit quicker. And so we're going to be starting with measurements today. So technically it's not stuff that you have watched already. But also you should be okay either way. So. You guys are going to be amazed by my drawing skills today. Let's see. Let me draw. What shall we draw today? How about a little leaf? Yes, that will work nicely. Looks like a really ugly football, actually, but the nature of energy. I'm going to talk about energy more when we get to chapter 5, I think. So we'll deal with energy later. Okay. Alrighty. Yep, so measurements today. So, I want you guys... Oh, Oz. Can you guys hear him? Actually, I don't think you can because this mic is pretty, close. Yes, we are certainly going to be doing math. Math and sig figs. It's all our favorite things. Or rather, things that you will learn to hate. You did hear them. Okay. Oh, well. Yeah. He's, 14 and hears things that aren't there, so... Oh, well. Okay, so... When we are measuring things, if we were to measure the length of this leaf, what would we be able to say this measurement is? Let's say these are centimeters. This is a really big ruler that only is 3 centimeters long, which is, like this much. But whatever. We have a very small ruler for some reason. If we were to look at this, would we say that this is 1 centimeter long? I hope not, because the 1 centimeter line is pretty far away. And obviously it's not 0 centimeters, right? We can see it's between 0 and 1 centimeter, right? Yes, Kevin. I would tend to agree with you. So, what we're going to do when we take our measurement is we're going to kind of use our best guess as to how long this particular leaf is. So, as Kevin said, I would say, about 0.8 seems to be, a pretty good estimate. However, let's see if I can duplicate this thing here. I'm just going to use different colors for our little lines here. 1, 2, 3, 4. 1, 2, 3, 4. And our leaf goes back on. Ugly football leaf thing. Hey, that's actually pretty close in size. I did a good job. All right, so with this particular measurement, we can see, first off, what do these two lines represent? And of course, if anybody can't see those colors, let me know. I will avoid them in the future. So they are kind of, I mean, yeah, but like what numbers are with those? Let's just use centimeters for now. Yeah, those would be like 1 millimeter apart for sure. You guys are right. But number-wise, yeah, that's what I'm looking for. We know that this is between 0.7 and 0.8 centimeters, right? So before, we could only see it was bigger than 0, less than 1. However, with this more accurate ruler, we can see it's between 0.7 and 0.8. And maybe, we would... I guess I can't... Oh, could I zoom in? Oh, how cool. I've never done that on this thing. We can see that maybe, I don't know, that's around 70% of the way between those two. Maybe thereabouts. So this thing might be around 0.77 or so. Thereabouts. So we're going to see that more accurate instruments give more accurate measurements. Okay, and so we also know that we kind of guessed on that 7, the second 7 there. We knew for sure, 100% certainty, that it's between 0.7 and 0.8, right? We could see that. We see those lines. We know exactly where those are. We know it's between those. So it's bigger than 0.7, smaller than 0.8. However, we do not know exactly how far it is between those two numbers. We're going to do our best guess based on the information that we have from this ruler. And so we're always going to see that the last digit in any measurement is going to be uncertain. All right, we're going to do our best educated guess as to what that number is, but it could be 0.76, it could be 0.78, right? Like, could be. It just depends, how far I can zoom in on this thing for us to really, make that call. Okay, but 0.77 seems pretty reasonable. It's just understood by everyone in science that last number, the second 7, is uncertain. Okay, so that's kind of our big takeaway here. The last digit in all measurements is uncertain. So with this very first one, in fact, we have no idea it's 0.8. We're guessing, and that's uncertain. We know it's bigger than 0, less than 1, 100%, but we do not know exactly how big it is. All right, with a better instrument, a better ruler, we're able to see that this is around there. Yeah, of course. If I were to give you something like this on an exam or whatever, or a quiz, and be like, what do you think the length of this thing is? You better be between 0.7 and 0.8 for sure. I would also, probably accept anything from like 7.6 to 7.8 here. I'm sorry, 0.76 to 0.78, thereabouts. Totally in your eyes. However, we have the idea also that it's not 0.71, right? We know it's not that close to the 0.7 mark. We know it's closer to the 0.8. So, I would hope that you're not guessing 0.71 for this one, if that makes a little bit of sense. So yeah, there will be a little bit of variance depending. And that's why these are uncertain. Okay, does that answer your question? Hopefully. Okay, cool. So, okay, and let's see. Okay, fun fact. Normally we would do this with grad cylinders in lab. We're going to see that many liquids form a meniscus. So, if you were to look at, let's say you have, a thin piece of glass at home, you'll be able to see that if you look really closely, the water or whatever liquid is in there is going to kind of creep up on the sides a little bit. All right, and it's going to kind of make this like U shape almost. And that is called a meniscus. And when we are measuring liquids, we always read the bottom of the meniscus. So that means we are going to take our measurement from the very bottom. So let's say that's here. We're going to want to understand that we are going to be measuring this to that point. We're not going to go up to the top of the little blue part. We always measure liquids from the bottom of the meniscus. Okay, the lowest point in there. Okay? So, with that being said, we know for sure this liquid is between 30 and 40 mLs, right? Definitely. And so, again, we're going to kind of do our best estimate here to try and figure out just how, or how full this particular thing is. So looking at that, we would say it's, between 30 and 40, for sure. And maybe, what do we think this is going to be? Again, we're following that kind of green line. Yeah, I would say it's, 34, 35, somewhere around there. Yeah, for sure. Let's say 30, who said it first? 34 was the first answer. I'm fine with that. So, that's the idea here. We're going to kind of... so Star-Lord, that's interesting. What you have done here. This will be an interesting point here. So, why does the 34.5 not make as much sense? 34.5 as a number... Remember, the last digit is always uncertain, which tells us that these two are certain. So in order for you to make that distinction that it's 34.5, you have to be absolutely sure it's above 34 and below 35. And from this particular instrument, because we do not see exactly where 34 and 35 are, we cannot say that this is exactly 34.5. Not going to work. What's better here is to say 34 or 35. Either one, because that tells us this 4 is uncertain, but the 3 is definite. We know for sure between 30 and 40. So I'm really glad you said 34.5, so I can explain to you why that's not the one to make on this particular example. Does that make sense, though? If, however, our fancy thingy did have, back to orange. I'm kind of a terrible artist, but if we did have those smaller ones, and we could see, oh yeah, that's where 34 is and where 35 is, then we could maybe say 34.5. But for right now, just don't have enough information to make that call. And so we're going to see that this uncertainty will carry over into all of our calculations. So every time we're going to be doing a calculation in chemistry or physics or whatever science you're doing, we have to be able to convey how certain we are about our measurements. Because if we're going to be using a really crappy instrument to do our measurements, we're going to end up with really crappy data, right? If your instrument can only measure, the difference between 1 pound and 2 pounds, but can't measure, 1.254 pounds or something, it's gonna be understood that any math we do with that 1 or 2 pounds is going to be uncertain. So if we were to try to calculate the calories from that or whatever, something like that, we would not be able to get a very accurate measurement there. And so we have a system called significant figures, which allow us to convey this uncertainty. And so any number that we're given in chemistry or physics or whatever will have, an amount of uncertainty associated with it, right? That's always the last digit. We know that, 34 versus 34.321256, obviously the number on the right is more, accurate, right? Assuming that, the instrument is good, we understood that this is the uncertain one and that's the uncertain one. So having more decimal places, we are more confident in our answer. That's a more, precise number on the right there. So that's better data. And so we have a system to be able to convey this information when we're doing calculations. And so in order to find out how many significant figures a number has, we have 4 rules. So the first rule is any number 1 through 9 is significant. Always. So if we look at the number 34, the 3 is significant, the 4 is significant. All right, those are both numbers 1 through 9. This number here has 2 sig figs. The number on the right has 1, 2, 3, 4, 5, 6, 7, 8 sig figs. 8 is bigger than 2. Hopefully you know that. Hopefully I know that. And as a result, the one with 8 is going to carry more significance into our calculations. All right, so hopefully rule number 1 here is okay. Anything 1 through 9, any number is going to be significant. Alrighty. We can also say any 0 in front of a number is not significant. And I'm just going to go ahead and move down a bit because I want to keep our rules kind of in one place, but I just want to do an example down here. If we look at these numbers, we are not going to ever count zeros that are in front of other numbers. So for this number, we are going to count these 3 to understand that this number has 3 significant figures. The zeros do not count. Okay, any zeros that are called leading zeros ahead of our number do not matter for us. And same thing here. Although this would be very strange to write 003,164, it's strange, but that will only have 4 sig figs. Okay, it does not matter if there's a decimal. Most of us would never write this number on the right. We would never say, 0, 100,000, 0, 10,000, 3,164. But we could. Technically, mathematically, that is totally allowable. But that's why our sig fig rules are going to be here. Okay. Back to blue. Any 0 that's between significant digits is significant. And what we mean by that if we have these 2 numbers, for example, the zeros in between are going to be significant. Okay, so zeros at the front, never. Don't even worry about those. Zeros in between other significant digits will always be significant. So as a result, this one will have 4 sig figs. And now this one we have multiple zeros here. Remember that these zeros at the beginning we are not going to ever worry about. Okay, so the 2 is significant. Let's go ahead. We see that all these non-zeros will be significant, right? And rule 2 tells us, rule 3, because I can't count, any 0 in between significant digits is also significant. Let's look at these zeros. The first 2 zeros, there's nothing on the left for them, so those are not significant. The 0 in between the 2 and the 1 is between 2 significant digits. We're good. This one also in between. And if we look at these 2 zeros, they're also in between 2 non-zero numbers. So those will be significant as well. So we count them all: 1, 2, 3, 4, 5, 6, 7, 8. 8 sig figs for this number. All right, any questions on those 3 rules so far? Okay, if there are, you can go ahead and type them out. And I'll just write this before we, I'm sorry, these other numbers, they have to go away now. I hoped to have made enough room, but I didn't. Oh well. The last one is the tricky one. Zeros that are at the end of a number are only significant if there is an explicit decimal point anywhere in the number. What I mean by that is that there is a difference between 20 versus 20 with a decimal versus 20.0. We're going to be able to say that the one on the right is the most significant. It has the most certainty of any of these digits. Numbers, rather. So because the one on the left does not have an explicit decimal point, only the 2 is significant. So this number has 1 sig fig. The number here, because there is an explicit decimal point, the zeros at the end will be significant. So that one has 2 sig figs. And our third one, again, all zeros at the end of a number are significant if there's a decimal anywhere in here. So this one will have 3 sig figs. So 1 sig fig, not as accurate or precise. The one on the right, 3 sig figs, is going to be more significant, more accurate. Give us more information. So those are the tricky ones. So let's do a couple of examples here. So it's still 3 sig figs. I mean, it you know, it's totally it's just depends on you know, numbers you're comparing, for example. So Savannah, it will have 3 sig figs. So it will be more accurate than a number that only has 2 sig figs. It will be less accurate than one that has 4 sig figs, if that makes sense. Okay, so first number here. How many sig figs are we going to say this one has? So, Savannah, the zeros at the front of the number are never significant. Only the 2, 0, and 1 will be significant for the number that you wrote there. So interesting. So far we have 7 and 3. Aha. And then we have 5. And a lot of people with 5. I would agree with the 5. So let's work through this. We know for sure, sorry, I'll be consistent, I will use blue. We know these non-zero numbers have to be significant, right? So there's at least 4 in there. Now we want to look at all of those zeros and see if they are zeros at the front, zeros in the middle, or zeros at the end. So the 0 between the 4 and the 6 is a 0 in the middle. Zeros in the middle always count. So, yes on that one. Okay, the other zeros in this number are zeros at the end. And so we have to ask ourselves, do we see a decimal point in this number? is one explicitly written out for us? Do we see one there? I do not. So these ones do not count as significant. Alrighty. So if we count up the number of blue dots we have, this one should be 5 significant figures. Alright, how about the second number? What do we think for this one? Nice, Kevin. Yep. Very, very nice. Very nice. Okay, I would agree with you. So, of course, these three, yes, for sure. We look at the zeros in the front. We remember zeros in the front do not ever count for significance. And then we see we have a 0 in the middle. 0 in the middle does count. So that one has 4 sig figs. Alrighty. Next number, 0.0400. So, for sure, the 4. So we now have zeros at the front and zeros at the end. Oh, I guess I can be consistent here. Remember, zeros at the front, never. So zeros at the front, never. I have tricked some of you. We do have zeros at the end, and the rule says yes if there is a decimal, no if there is not a decimal. So does this number have a decimal point that's explicitly written out? I see a decimal point. So right over here. And because there is an explicit decimal, these zeros will count. So overall, we should have 3 sig figs. Okay, and don't be, ashamed or anything if you're getting it wrong. Like, that's why we're here. We're learning. We are supposed to get things wrong so that we can learn and do better. Next number, 0.612. Yeah, this one's easier, huh? 1, 2, 3. We have a 0 in the front. 0 in the front never counts. 200. Just 1. Absolutely. I got some of you. Now, what's interesting, 2 sig figs. How would you get 2 sig figs? I'm curious. Okay, well, that's okay. You don't have to explain. So this should be 1 sig fig because we see the numbers at the end. We do not have a decimal. So if it were 20 with a decimal point, it would have 2 sig figs. But because there's no decimal point in this one, those zeros will not be significant. Okay, so because no decimal. No decimal means they don't count. I see. So any zeros that are at the end. So, for example, if we look at the next one, 8, 1, and 2 are significant for sure. Are the zeros significant? They should not be because there is no decimal in this number. And so none of those zeros matter. So this number will also only have 3 significant figures. Those are our rules, that's why. So, the reason that these don't matter is because those zeros are placeholders. Yeah, if there were a decimal, all three would be significant. Remember, any decimal anywhere. Aha. Aha. Let's look at that. Let's look at that. Because that's how we're going to be able to convey our certainty about the measurement. If I say there are 3,000 people at Cerro Coso right now, is that number very accurate? Probably not. I'm probably just making an estimate. I know it's probably between 2,000 and 4,000. I'm going to guess 3,000. Right? However, if I say there is 3,002 students at Cerro Coso right now, that indicates to us that I have counted 3,002. This number is more accurate than just saying 3,000. However, if I were to count every single student and there were 3,000, I could say 3,000 with a decimal point. And that lets you know that I counted 3,000. I know that this is just kind of a guess. And this one tells us I've actually counted. Oh no. Oh no, we have lost the tablet. Alright, let me fix that. So, this is the reason that we have these numbers. So yeah, we absolutely have the placeholders, right? If we go back up here to 200 versus 2,000, they're both uncertain numbers, right? However, these zeros are here to tell us it's 20,000. 20,000 is not the same thing as 2. Would you rather have $20,000 or $2? I hope you make the right choice there. However, those zeros are important to let us know that this is a bigger number than just 2. However, it is uncertain. Okay, these both have the same amount of certainty. There's 20,000 people at Cerro Coso. Probably a guess, right? So the number that we'll get from our instrument will tell us if we have a decimal or not. And so as a result, we will know if these zeros are significant in that those were measured zeros, or if these were guessed zeros. So if we had just guessed that they're there, or, you know, we needed them to talk about the significance there. So there is a method to the madness here. These zeros are important in 812,000, but they are not significant. We know that this is our last certain digit, or I'm sorry, that is the uncertain digit, the 2. The rest of the zeros are not really part of the significance. They're just there for placeholders. Okay, to let us know it's 812,000. There are ways to make this easier for us, and we can do that by displaying numbers instead in scientific notation. This will help eliminate some of the confusion when it comes to having extra zeros around. So we know we had that 812,000 before. I can tell you mathematically that is the same thing as saying 8.12 times 10 to the 5th. Not lying to you there, that is true. And by doing this, I've gotten rid of those placeholder zeros. And now we can see much more clearly that this number has 3 sig figs. It still has 3 sig figs over here. But by putting it in what's called scientific notation, we've kind of eliminated that ambiguity. Aha. Okay. So, if we do 8.12 times 10 to the 3, that is 8.12 times 1,000, right? And so that would actually be 8,120. All right, so that's not correct. If we want to think, yeah, so I think you guys have gotten it right there. We could say this. That would work. However, we're going to see that we prefer, these are accurate. These are the same number. All 3 of these are the same number. However, with scientific notation, it's standard practice to only have one number before the decimal point. And so, even though there is no decimal in this 812,000, we know it should be here, right? If we were to write it out. And so we would have to move it 1, 2, 3, 4, 5 times in order to make it so we have one number before our decimal point. And as a result, that's why it's times 10 to the 5th. Okay, again, mathematically, 812 times 10 to the 3rd is accurate. However, with scientific notation, we want to only have one number before our decimal point. So, what am I doing the same number for? Let's take some of these other numbers that we have here. Okay. So we remember before, this number had 4 sig fig, this number had 3 sig figs. Right? Same numbers from before. But let's go ahead and convert these into scientific notation. So that means we are going to move the decimal such that it is going to have one number to the left of the decimal, a number 1 through 9, and all the other numbers are going to be on the right side. Yeah, I like it. So we're going to move it over 2 times. And because this number is small, less than 1, it's going to have a negative exponent. Beautiful, beautiful, beautiful. Notice that this number still has 4 significant figures. I have not changed that by putting it into scientific notation. And so you may be tempted to say, okay, well, this is, going to be the same thing. It's 4 times 10 to the negative 2. However, we have now lost some significance. We're not going to say that because that number only had 1 sig fig. We had 3 sig figs before we messed with the number. Let's keep that. Exactly, Savannah, that's exactly what I'm going for here. So this should actually be 4.00 times 10 to the negative 2. And so as a result, we still have 3 sig figs. This one only had 1, so that's why that is not going to be our answer. Okay, so when we change numbers into scientific notation, Savannah, you're absolutely right. We must keep our sig figs. Alrighty, let me look at another number here. Let's see. Okay, let's do this 8140600. Oops. Yeah, exactly. So that should also be exactly another like hint that you're doing it correctly. So if we look at this number, we saw that this had 5 sig figs, right? Because we did not have an explicit decimal. However, we know where the decimal would be if it did have one. And so if we're going to move this over 3, 4, 5, 6 times. Beautiful, Star-Lord. Beautiful, beautiful, beautiful. What was it, 10 to the 6? Yeah, I think so. Yeah, 6. Perfect, perfect, perfect. And so, again, this rids us of having those pesky zeros that are used as placeholders. In this example, up top, the 0.0400, we got rid of those zeros at the front. And in the second, or the last example down here, we were able to get rid of those zeros at the end that weren't significant either. So by putting it into scientific notation, we can kind of avoid a lot of these confusing parts. And so we'll know that in scientific notation, every number that we have should be significant. So it would be wrong because if you only had 8.14, we count the sig figs here. If we had 5 before, we better have 5 now. So that's why we're not going to just put 8.14. Okay. Cool, cool, cool. So, based on this, I think I am lying to you. I will probably give you an assignment tonight just to reinforce the sig fig stuff. So all of you who have been begging for homework, I will have a relatively easy assignment for you guys to do with these sig figs and measurements. Okay, so I will be posting that up to Canvas for you. I know, oof, indeed. But hey, it was just an assignment you would have gotten next week, so oh well. You'll just do it now instead. Alrighty, I know. No, sad times. Sad times. Okay, do we have any kind of outstanding questions on how to count the number of sig figs that something has? Yes, the suffering begins. You'll see sig figs will plague you for the entirety of your chemistry career. So, you'll be having nightmares about sig figs. You'll be in the shower crying about sig figs. It's normal. Welcome to chemistry. And it's only just beginning. The sig figs are just beginning. Okay, let's just quickly do how to go from scientific notation into regular numbers. Let's say I had this. Oh, good. Post the meme in our Discord so we can all enjoy it. Okay. Perfect. Okay, I will look at it later. Okay, so if we want to go from scientific notation to regular notation, for some reason, we could do that as well. We just kind of have to do the opposite process. So if we look at this first number, 6.02 times... Okay, you guys are too fast. Okay, negative exponent means small number, right? Small number means we're going to move our decimal point over 4 times such that we get... yeah, you guys are right there. Notice we started with 3 sig figs here. we still have 3 sig figs here. Hopefully the pattern is clear for you guys. And if we were to do this one, we see 8 or 10 to the 5th big number. So we'll take our fake decimal point and move it over 5 times. Or in this case, we just add 5 zeros to it. Notice 3 sig figs. Notice 3 sig figs. Rather, S sig figs. Yeah. Kevin, you're absolutely right. This number, in fact, you are right, is not in scientific notation, and 8.22 times 10 to the 7th would be the correct way of doing the scientific notation. How does the bottom have 5 sig figs? This one here? Sorry to is this the number you're talking about? Like this one? Okay, cool. Never mind then. Oh, maybe it was the S sig figs. Oh no, Google has found out. Okay, so that should also not be too difficult. Alrighty. So, let's go ahead and finish today off. Maybe I don't want to give you the homework right away. I'll think about it. We'll see. Okay. Let's say we had these 2 numbers. Oh no, let's not use those 2 numbers. Let's say, yeah, we had these. Okay. Or whatever, I'll just make up numbers. Was it 10 to the 6? I don't even know. Alrighty. We'll see. Okay. So if we were to do this math, we can go through it. We could, of course, plug these into our calculators, work on it that way. Probably an easier shortcut to do this is to make it something like this. Because this part on the right is super easy to do in your head, right? That's 10 to the negative 10, right? If we put that. And if we want to put things in your calculator like this, it's going to take a long time, parentheses 6.00 times 10 to the negative 4, close parentheses, divided by parentheses 8.1406 times 10 to the 6 parentheses. That's annoying. A lot easier to just do 6.02 times or divided by 8.1406, right? So, if we do that, bust out your handy dandy calculator, which is going to be most likely, your phone or Google. Google will do a good job too. 140. Shut up, Google. Okay. We see that this number is 0.7395033230. You are getting ahead of us, Kevin, and I love it. Okay, great. You have exactly the right answer. When we look at this number, we remember we had 3 sig figs up here and 5 sig figs up here. This number has a cajillion. I don't want to count that many, that's why. However, that's telling us now that our answer has quite a bit of significance. What we want to do anytime we're multiplying or dividing numbers with sig figs is we have to take the smallest number of sig figs. Alrighty, so what we're going to do is we're going to look at this and let me just write this out. When multiplying or dividing, take the lowest number of sig figs. So, between 3 and 5, I would say 3 is lower. So, in fact, we do not have a cajillion. we should have 3. And the 3 that we're going to want to keep are the biggest 3, right? We want to keep the ones on the left. So we remember that guy, never significant, right? Boop, boop, boop. We want to keep 3. So we're going to keep the 3 on the left, the leftmost 3. And now what we're going to want to do is we look at the next number, because we're going to round this, in fact. So we see it's a 5. The rule for rounding is if it's a 5 or higher, the next number, we're going to round up. If it's a 4 or less, we are going to round down, or in fact just get rid of it. So remember, we're keeping 739. So we look at this one and we round here based on this 5. Because we looked at the 2 numbers that we divided. One of them was 3 sig figs, one of them was 5 sig figs. We always want to take the lowest number. So in this case, that would be 3 sig figs. If that makes sense. And so we have, I'm sorry, I'm going to have to skip over this. Oh, we'll do it in blue. We had 0.7. And so if it's 5 there, we're going to round up, right? So that's going to push this to 0.740. We round it up. Okay, don't forget we still have this dude chilling out on the side. The exponentials do not carry significance, so don't ever worry about sig figs with the exponents. And as Kevin so wisely did, he thought, okay, well, let's just go ahead and fix this scientific notation, because technically we would want to move our decimal over. And so that would actually be 7.40 times 10 to the negative 11. So that one, if you look at this part here, 10 to the negative 4 divided by 10 to the 6th is 10 to the negative 10. Remember, when you're dividing exponents, you subtract the numbers. We can do a little bit of practice with that as well. So remember, 10 to the negative 4 divided by 10 to the 6th is 10 to the negative 4 minus 6, which is 10 to the negative 10. Cool. And remember, with multiplying exponents, you would add them together instead. Okay? So, all this hard work we did, we looked at the sig figs of our original numbers. We saw that there was one with 3 and one with 5. So we chose the one that had the smaller number, and we ended up rounding our final answer to have the same number of sig figs as our least significant number. So whenever you're multiplying or dividing, we always take the negative, or the lowest amount. So with that one, Bailey, these two numbers are mathematically equivalent, right? So if I didn't explicitly say, let's put this in scientific notation, either of these is fine. But since Kevin is our master question answerer here, he has already put it into scientific notation for us. And so since we had to move that decimal one place over, we just had to adjust our exponent accordingly. We moved our our decimal one place to the right, so we have to reduce our exponent by 1. So it goes from 10 to the negative 10 to negative 11, just by moving that. Okay? We've got time for one more. Let's do this one. If it were 5, we would round this to 0.73950 times 10 to the negative 10. Okay, let's do more. More. You know what? Let me get rid of this 0. I don't like it. You could put it in scientific notation. Yeah, with 5 sig figs, that would be 7.3950 times 10 to the negative 11. If it were 5 sig figs. Oh, this one actually we could just do in our heads. We don't even have to use a calculator. Alrighty. So, let's look at the sig figs. How many sig figs in the first number? We should have 4 sig figs here, right? This number here should have 2 sig figs, and exponents don't count. Yeah, it just depends on what your significance is. So if we look at these numbers that we're multiplying, between 4 and 2, which is less? I hope 2 would be your answer. So we know mathematically we do this. If we do the math, it's that. Or if you were in scientific notation. However, we need... Oops. We need only 2 sig figs. So we're always going to start on the left. We're going to say, okay, oops, I need this one. I need this one. That'll be 2. 2 sig figs. All right, or if you're doing in scientific notation, same thing. You would take those 2. And so now we look at the next number. That's a 1. Is a 1 going to round up or down? Remember, if it's 4 or less, we round down. 5 or above, we round up. So we're going to actually round this one down. Which tells us that this number is 26,000. Or if we kept it in scientific notation, 2.6 times 10 to the 3. So because, Gerson, the numbers that we started with, we always want to use the least number of sig figs. So the first number had 4 sig figs, second number had 2 sig figs, and the third number didn't have sig figs. So we always want to choose the lowest one. And so that's why we're using 2 sig figs. So depending on... Wait a second, this should be 10 to the 4th. I lied to you guys. That's why. So we need 2 sig figs because 4 sig figs versus 2 sig figs, we always have to say the not significant one. Yeah. Sorry. Yeah, sorry. I didn't. I'm bad with the counting as well. So we're okay. Okay, if our number were, if we had 26640 and we needed 2 sig figs, just to see what that would look like, we would look again, we would say, okay, we're keeping these 2. We look at the next number, that tells us round up, and so our answer then would be 27,000. Okay, so if we were to round up, I was just showing you how to do that. So we always look at the number next to our significant digits and we round it there. Okay, so we are out of time today. So we are going to continue our Sig Fig fun and horror on Monday. We're going to then do more math with these things, and we're going to play with our Sig Figs, and then on Monday or Tuesday we will have some... we didn't use 5 Sig Figs, we used 3. Gerson. Yep, no worries. Someone would just asked if it were 5 Sig Figs, what would it be? So that's what it would be. Okay, so I understand. Lots of stuff that, why is it to the 4th? Because math? That's just the way that it goes. I mean, if we look at the 1, 2, 3, 4, 4 spots would be why it's to the 4th power. Okay, so just gonna erase that. Yeah, no worries, no worries, no worries. I understand, brains are fried. Yeah, exactly that too, Kevin. Exactly. You know what? Kevin's gonna teach the class now. He's better at math than I am. So, yeah, Kevin will do it for us. Okay, so yeah, we will see you on Monday. Right. Just try and review this stuff. If it is completely mind-boggling, like what the heck, I still have no idea about these sig figs, just like Google Khan Academy sig figs. Google that. You will have plenty of practice to go through. Correct. We are not having lecture tomorrow this week, but next week we'll probably have a Thursday lecture. Okay, so for us, we are done until Monday. Yeah, Monday's not Labor Day. That's the week after. So Kara and I decided probably not. I'll let you guys know. I will ping you on Discord and upload something to Canvas if I decide to. But I'm leaning on not doing it right now. Okay? Okay. Enjoy your weekends, everyone. Dream about sig figs. Start having the nightmares. Tears are okay. I am fine with crying in the classroom. So, have fun. Okay, see you guys. Take care.